Bismillahirrahmanirrahim. Now we will be discussing those dynamical systems where eigenvalues are complex. And in particular, first we will consider the case when eigenvalues are purely imaginary. Eigenvalues are purely imaginary. And specifically, first we will discuss this form: x prime of t to be equal to 0 beta minus beta 0 times x, or maybe you can say that x prime is equal to beta times y and y prime is equal to minus beta times x. So this is kind of dynamical system that now we will study. We will see that what are its eigenvalues. In fact, they are going to be purely imaginary, and then we will find corresponding eigenvectors. Then we will be discuss a bit about solutions to such kind of systems, and finally we will see phase portrait for this kind of systems. So let's begin with what we call the eigenvalues. So in fact, in this case, A is this 0 beta minus beta 0. I'm interested in the eigenvalues of this matrix A, and for this I need to find determinant of A minus lambda I to be 0. So I can have minus lambda beta minus beta and then minus lambda to be 0, which gives me lambda square plus beta square to be 0. And that shows that eigenvalue lambda is nothing but plus minus iota beta. So I can say that lambda 1 is, let's say, iota beta, and the lambda 2 is, let's say, minus iota beta. But I'll first talk about eigenvector corresponding to this eigenvalue, and then we will see that it's enough to only find the solution through this one particular eigenvalue. So let's begin to find eigenvector corresponding to lambda 1, that is iota beta. And we know that to find eigenvector we need to solve A minus lambda 1 times I, all of this applied to an unknown vector x to be 0. We need to solve this system for finding eigenvector. So this gives me my A is 0 beta minus beta 0, and this is going to be lambda 1 0 0. Lambda 1 is basically iota beta, so I can write iota beta here and iota beta here. So all of this is applied on xy column vector set to be 0 0. And from here you can easily find out that it's going to be minus iota beta beta minus I beta times xy to be equal to 0 0. And from here you have two equations, and it's not hard to show that these two equations are multiple of each other. If you multiply first one by minus iota, you can get second one. So like it's enough to consider only one of these. So let's consider this, which is minus I beta x to be equal to minus beta y, which can be simplified. This gets cancelled, minus gets cancelled with this, y to be ix. And if I set x to be some t, then y is going to be I t or iota t. So therefore my solution has to be x of t to be equal to t I t. Or if I pull out this t, then I have 1 and I. So all of this gives me eigenvector to my corresponding to my eigenvalue lambda 1 is from here x of t to be t times 1I, and from here, I mean, if you are even not putting this t because this is just x that we were solving for, from here you can easily see that this is going to be the eigenvector. So the eigenvector is v, which is 1 and I. Okay, so from the solutions construction to the differential equations, how we construct solutions to differential equations, we already know that the solution to this particular system is then given by x of t to be equal to e to the lambda 1 t times v. So this is going to be e to the iota beta t times my v, which is 1 and I. Now, do you realize that this differential equation was an real system and the solution has turned out into the complex numbers? So we can somehow manage to convert the solution to real numbers, a real system. And how can we do that? We can just apply the so-called Euler's formula to this Euler's formula. And what does Euler's formula says? It says that e to the iota beta t is nothing but cos beta t plus I sine beta t. We will use this in place of this, and then we can see something interesting coming out. Let's see that. So the solution may be written as x of t to be equal to cos beta t plus I sine beta t times 1I, and it can further be simplified to write cos beta t plus iota sine beta t. Then I have minus sine beta t plus iota cos beta t, which can further be simplified to write cos beta t minus sine beta t plus I sine beta t cos beta t. If I label this one as the real part of the solution xre of t, and this one is imaginary part of the solution x imaginary of t, then my solution can be written as x of t to be equal to real part plus iota times imaginary part of the solution. Okay, so in fact it's not hard to show that these both solutions, real part and this imaginary part, these separately solve the system. In other words, these both are solution to the original system. You can in fact verify this. X prime of t is going to be equal to time derivative of real part plus iota times time derivative of this imaginary part, and this is going to be equal to a times x of t, which is derivative of real part imaginary times derivative of I times derivative of imaginary part, but this x is going to be this guy. So a times x real part of t plus a times imaginary part of the solution, which is going to be equal to the derivative of real part plus I times derivative of imaginary part. And from very basic properties of complex numbers, this part is going to be equal to this. In other words, x time derivative of real part is going to be a times real part, and derivative of imaginary part is a times imaginary part of the solution. So these both are separately satisfying the original equation too. And because these both are the solutions, so we can expect their linear combination to be the general solution. So the general solution general solution to the system, which system? This one, 0 beta minus beta 0 x, is going to be x of t to be equal to c1 times real part of the solution plus c2 times imaginary part of the solution. Now this solution is not involving any complex number, and it's not hard to show, to conclude that this is the general solution. Like, it's enough to consider one eigenvalue, which was lambda 1, like we consider iota beta, and construct eigen vector corresponding to that, and from there you construct a solution, and from there you construct imaginary and real part, and then you can just find their linear combination, c1x imaginary plus c2x real part, and that's it. That's the solution to this system. Okay. So now, next thing that we want to discuss is next thing that we can discuss is phase portrait. And phase portrait of this system, 0 beta minus beta 0 times, and for this you need to wait for the next session.